Hello and welcome to our Data Science for Ecologists in R series. Today we will talk about the normal distribution. Although this is probably nothing new for many of you, we will shortly discuss the basics because it is such a fundamental part of many statistical models that will be discussed in this series. To better understand the normal distribution, I would like to briefly introduce the closely related concept of a random variable. As the name suggests, this is a variable whose value is decided by chance. For example, if you randomly select a woman from Germany to measure the height, it depends on chance which height you will observe. Therefore, the height is a random variable in this case. Although it is unclear which value will be observed exactly, some values are more likely than others. For example, you would rather guess that the observed height is 1,70 m than 1 meter or 2 meters. This is because the height has a certain distribution in the population of German women. Okay, now we can already give the most general answer to what the normal distribution is. It is simply one possible distribution that a random variable can have. Let's now dive a little deeper. You've probably all seen this bell-shaped curve before and know that it reflects a normal distribution. More precisely, it turns out that this curve is the graph of the so-called density function of the normal distribution. This density function is given by this formula right here and defines how likely different x values are. Admittedly, it looks a little complicated, so let's only focus on the important parts, mu and sigma squared. Mu is the mean of the distribution, and sigma squared is the so-called variance, which defines how much variation there is around the mean. When a random variable x follows a normal distribution with mean mu and variance sigma squared, we express this by writing x tilde n mu sigma squared. Before we discuss the mean and variance in more detail, we should first come up with an intuitive way to think about the density. For this, let's look at a normal distribution with mean 0 and variance 1 and randomly sample 10,000 data points from this distribution. The reason why we sample so many data points is that we want to get a precise picture of the whole distribution, and obviously this is not possible if we draw a very small sample. The first value we obtain is around -0.7. Then we get a value of around 0.2, and we continue sampling until we have all 10,000 data points. You already see that this way of representing the data is quite messy because many data points are on top of each other and we can't really see anything. So instead, we choose a histogram to represent the dataset. Here, the height of individual bars represents the absolute frequency within different intervals. For example, a little more than 400 data points lie within the interval from -0.1 to 0. Let's now draw a connection between this histogram and the density of the normal distribution that we used to sample the data. For this, let's rescale the y values of the histogram such that the total area of all histogram bars equals 1. As you can see, the y values get smaller, but the shape of the histogram stays exactly the same. Therefore, this rescaled histogram still represents the distribution of our sampled data. Let's now plot the density of our normal distribution with mean 0 and variance 1 for all x values from -4 to 4. The resulting graph matches the histogram quite well. And in fact, we can think of the density of a distribution as the histogram that we obtain if we sample a very large, or more precisely, an infinite amount of data from this distribution. Let's now take a look at how the two parameters affect the shape of the density. Changing the mean simply shifts the whole distribution along the x-axis, such that the center of the distribution corresponds to the mean. The variance influences how much variation there is around the mean. If the variance is small, most of the data are close to the mean, and values that are far away from the mean are unlikely. With bigger variance, the distribution becomes wider, such that large deviations from the mean are more likely. Now that we know what the normal distribution is, we should also understand why it is so important. Often, it is reasonable to assume that our variable of interest is the result of adding many more or less independent influences together. Given this assumption, mathematical theory tells us that in many cases the normal distribution is a good approximation of the distribution of our variable. As an example, let's suppose that we are interested in modeling the height of German women. Growing up, there are numerous diet-related and genetic factors that influence the height, and we can think of each factor as adding something to the height that is ultimately observed. Consequently, the normal distribution might be a good model for the distribution of heights. And in fact, this is what we observe in practice. Okay, after this short recap, we are now ready to start with the actual statistical modeling in the next video. See you soon!